These are the notes for the second day on 5.4. We're working on our derivatives of e and natural log in day 1. In day 2, we're going to be integrating expressions with e's and ln's. So it only makes sense that if the derivative of e to the x is e to the x, well then the integral or the antiderivative must also be e to the x plus any constant. Likewise, when I do the antiderivative of e to the u, du, again this is really important when we do u substitution, we need to write dx in terms of du. That's important. Let's put a set of eyeballs on there so that we don't make the mistake of reading this as being e to the 5x plus c. That's not what it is. And you might say, well, it says it's e to the u plus c. It is, but I have to write this in terms of du. So remember, if u is your 5x, du is 5 dx. And dx is a fifth. It's got a fraction correction of du, and we've gotten really pretty good about that. So this becomes 1/5 e to the 5x plus c. So be careful of that fraction correction. Now, the issue becomes what is u when you're working with these expressions? And there's a couple things to keep in mind. A lot of times we let u be the inner function. So when we take the derivative, it's the rest of the integrand, and we can use our power rule. A lot of times we let u be the denominator, because if its derivative is in the numerator, then when we integrate this, we end up getting the natural log. A lot of times when we have the exponential functions like e to the and 3 to the and those, we try letting u be the exponent. So there's lots of choices for u, and that's the frustrating part with integration, is because you're being given the answer and we want to know what was the question, and that can be a little tricky to figure out. So basically, if one u doesn't work, try another one. So on this one, I'm going to pull my constant out front because I like to, not because I have to. I'm going to let u be 1 minus x. What that would mean is du is negative dx. So if I can throw out a negative multiplier or a negative fraction correction, this is actually negative du. So I have 4 e to the u negative du. And now I can use my integration rule, which says it's negative 4 e to the u plus an arbitrary constant, which we like to call Carl. So on number 19, I could pull the 2 out front, but if you look at the exponent, it's x squared, and its derivative is 2x. So this is a straightforward e to the u du, which becomes e to the u plus Carl. And again, if ever you're not sure, just quickly take the derivative. The derivative of e to the x squared is e to the x squared times 2x, and it works out great. So number 20, is u the denominator? No, because the derivative is 4x. That's not even close to the rest of the integrand. Is u, the next thing I would try is letting u be the exponent. Let's let u equal 1 over x, or equivalently, negative 1 over x squared. I'm sorry, x to the negative 1. I was starting to take the derivative already. So du would be negative 1 over x squared dx. And you'll notice I have an x squared dx in the rest of the integrand. The half can come out front. I'm really integrating e to the 1 over x squared. So if I throw a negative fraction correction here, I do have e to the u du. So I end up with negative 1/2 e to the 1 over x, or x to the negative 1, plus Carl. And that's the end of it. All right, let's move right along to number 21. Let's throw in some trig integration here. So I've got a product. I've got some e's and some cosines. I'd immediately, again, you kind of have 3 general procedures for determining your u. It's an inside function, it's a denominator, it's an exponent. One of those is generally your winner. And there is no denominator here, and there is no inside function. So my last resort is let u be sine x. And let's hope that du is the rest of the integrand. And it is. So this is just a clear case of e to the u du, which becomes e to the u plus our good friend Carl. And I'm done. So for number 22, let's try letting u be, first of all, an inside function. Don't have one. A denominator, let's give that a rule. Let's give that a whirl. I would let u be 4 minus e to the x. My derivative of u with respect to x would be negative e to the x dx. And you'll notice that that is almost what is in the numerator. It's pretty darn close. My problem is I don't have a negative e to the x, so I'll just throw a constant fraction correction out front of a negative. So I get negative du is actually e to the x dx. So I've got a perfect case here of 1 over u du, or u prime over u, with a negative fraction correction. This becomes natural log absolute value of u plus my good friend Carl. So that's how that one would play out. Now I'm just going to keep rolling through these. Number 23, who is u? Well, inside function, not an option. Denominator, let's try it. Let's let u equal e to the x plus e to the negative x. When I take its derivative with respect to x, I get e to the x minus e to the negative x dx. That is the entire rest of the integrand. This is a fantastic case of u prime over u, or 1 over u du. That's natural log, no fraction correction even needed. This is the entire rest of the integrand right here. It's du over u, which is this format. So it's natural log absolute value of u plus our good friend Carl the constant, and I'm done. Let's go look at number 24. And if you've got u substitution on the brain, you're like, I'm going to let u be the bottom. Nope. I'm going to let u be the top. Nope. Oh no, how do I do it? If it makes a heart, you break it apart. So don't get stuck in doing all of them the same way. Every problem has its own little twists and turns. So that's why I do these worksheets instead of the book, so you can kind of get used to not doing just what's in that section. We're going to throw in right here a monomial on the bottom, and for that, we break it apart. Well, what is the antiderivative of e to the 3x? You might say e to the 3x. No, it's not. It's 1/3 e to the 3x. So be a little careful with that. The antiderivative of 2 is 2x. The antiderivative of 1 over e to the x, keep in mind that's e to the negative x dx. So that's minus e to the negative x. So be careful with that as well. We got to watch all our signs and all that good stuff. Why would that be? Well, because u would be e to the negative x, du would be the derivative of that, e to the negative x times the derivative, and then a negative fraction correction out front. So that one's done. All right, so now what we're going to do here is discuss how we apply this to stuff we already know how to do. Well, we are going to do a little area underneath a curve. I don't think I'll do all of these with you. Maybe just go to number 20 here. First of all, I would like to know what the graph of that looks like. If you go on your graphing calculator and graph it, it's going to kind of go like this. I am being bound by x equals 1 and y equals 0, and there should actually be another one here that says also bound by x equals 0. Let's throw that on there so that otherwise we've got what's called an improper integral. We're going to negative infinity here. So here is my region. And I'm just looking for area, so I'm not whipping this around. I've got no pi, no cylinder. Area is just all about the representative rectangles, and we're going to be adding up the area of those as we swing from 0 to 1 along the x-axis. So we don't need to memorize, we just need to figure out the base of every rectangle and its height, which is top function minus bottom function, but in this case, the bottom function is the x-axis. So it's really just up here to e to the x over 2 plus e to the x. Now, if I had a calculator, I could go math 9 it, but I want to keep this one exact. So what we're going to do here, and we'll just skip these two, they're kind of similar. If you can do one, you can do all of them. So what I need to do is figure out how I'm going to integrate this. Let's let u be the denominator. That's always a good bet. And its derivative is the numerator. So this is lovely u substitution. This is really just 1 over u du, where u is 2 plus e to the x. So this is going to be natural log absolute value 2 plus e to the x, going from 0 to 1. Absolute value could be chucked here because 2 is always positive, duh, and e to the x is always positive for all x's. So I could actually legally drop those absolute values. So fundamental theorem of calculus, we're going to put in our top boundary. That's going to give me ln 2 plus e. And I'm going to drop those absolute values since that's always positive, minus ln 2 plus e to the 0, which is 2 plus 1, or ln 3. Keep in mind you have to be good at playing with logarithms here because you might not see this, but subtraction can condense into division. So we'd have ln 2 plus e over 3 would be my best answer for that. Now I would challenge you to go math 9 this from the get, whoa, math 9 this, and it will give you the decimal version of that. You can verify that yourself on the calculator. So last up, I'm not going to do number 16. Let's go look at number 22. Let's go rotate some stuff. So we are going to do e to the x over 2, which goes through 0, 1. If you went on your calculator, it'd look kind of like that. And it's in the first quadrant, and we're cutting it off right here at x is equal to 2. So I am going to shade all that in, which I don't want to, so you can go shade it in. We are whipping that about the x-axis, so we draw a representative rectangle perpendicular to the axis of rotation. This is going to be a disk problem because it butts up right against the axis. So if you picture that, it's going to make this solid right here, and it's going to be completely solid. You can't put anything in it. And we're going to find the volume of that. So we're going to whip that around, creating those cylinders. A cylinder is pi r squared h, where my h is actually dx. And I need to integrate that from 0 to 2. So all I need to know is my radius, and it goes from the axis to the outer edge. There is no inner edge because it's a disk problem. So notice I didn't memorize that formula. Well, I do have it memorized, but I can create it if need be. All right. So I'm going to integrate from 0 to 2. My radius is e to the x over 2, and I'm going to square it dx. And we're going to do this by hand. So I'd have pi times the integral from 0 to 2. E to the x squared would be just e to the x over 2 squared would be e to the 2x over 2, or just e to the x. Super easy to integrate e to the x because its antiderivative is simply e to the x. So I've got pi times e to the x evaluated from 0 to 2. Be careful of always thinking that the 0 causes a 0 because e to the 0 is really 1. So be careful with that. We have to do pi times e squared minus e to the 0. And you can leave it like that if you would like to. And I would just write it like pi. I'm going to soften those brackets up a little bit. And that's my answer. So you will finish that worksheet. I believe it picks up from 22 on, I think. So we're on worksheet 5.4, the second part of it. Have a good one.